and they're training me. Okay, I wanted to get this on the recording. I'm going to record today's lecture, but if you're not here, and I'm not talking to you, but if someone listens to this and actually wasn't here, a lot of it is going to be up on the board. Okay, it's not going to necessarily be here. You might hear our voice or hear what's going on, but you might wonder what's going on. So we'll start, like I said, just back a little bit. This was a critical slide. I'm going back. Rules for writing electron configurations. Just to wake you up in the morning here, we mentioned this on Tuesday. What we're talking about is where exactly are these electrons? Where are they? There's energy levels, sub-levels, and then there are orbitals. So remember, there were energy levels, n equals 1, 2, 3, up to 7. Principal energy levels. And then within there, that is broken down into sub-levels, S, P, D, and F. We said, so please don't forget. There are sub-levels. And then within those sub-levels, there are orbitals. And an orbital can only accommodate 2 electrons. Electrons are negatively charged. They don't like to be kind of in the same space or vicinity. And the way they tolerate it is that they spin in opposite directions if they happen to have to go in the same orbital. So S only has 1 orbital, it holds 2 electrons. P has 3 orbitals, it holds 6 electrons. We didn't mention this Tuesday, but we did mention the maximum number of electrons. D has 5 orbitals and it holds 10 electrons, and F has 7 orbitals, 14 electrons. This is what you really need to remember, the capacity of those orbitals, of those sublevels. So that got us then to look at this a little bit. This is a graph or a table here kind of showing what is the energy associated with a certain sublevel. So this is the 1s sublevel. This is energy. What's the number here? We don't need to worry about that. This is the lowest. We're going from low energy to higher energy. So we're not going to worry about the actual number. But just know that this is lower than this, which is lower energy than this, which is lower energy than this. And then when we get past 3p, it starts getting a little tricky. That 3d, even though it's in the 3rd energy level, the 3d orbitals are slightly higher energy than the 4s. So big deal. What's the big deal about that? Electrons go to the lowest energy spot they can find before they start filling anything higher. Yes? This means yes. Or yes means yes. Okay? So they fill lowest energy first, and then they go up from there. So to deal with this, and I only went 4s, 3d, 4p, 5s, you can see they start getting all mixed up in there. Well, this unmixes them. Let's erase that for today. And this is on the back of your periodic table. So you're going to use both sides of this periodic table today. You're going to find the elements I give you, and now that most of you are here, let me see how we're going to divide this up.
I have one question.
Yeah, Joel.
So because we're going this way, diagonally this way. So that being said, do we start off with 2p and then 3s? Oh, yeah. All right, no. I answered my own question. Never mind.
Follow that line.
Yes, yeah.
Okay, this is like, what's the young lady in the Yellow Brick Road thing?
Wizard of Oz.
Wizard of Oz.
Yeah.
And who? What's her? Dorothy. Dorothy. We don't. I should have turned this yellow. Okay, just follow the Yellow Brick Road. Okay, just follow that path. And where do you start? Here is where you start. Okay, this is kind of like one of those mazes, and you say, start here. Okay, get through this maze. Well, this isn't a maze. This is a fairly distinct thing. Now, keep this in mind. Memorize these numbers. Know this. That I don't care where the S sublevel is, first, second, third, fourth, fifth, sixth, or seventh energy level, it can only hold 2 electrons. That doesn't change from energy level to energy level. P can hold 6, D can hold 10, and F can hold 14, whether it's a 4F or a 5F. You can see that the third energy level does not have an F. Doesn't have an F. And that's where we get the fact that that first energy level can hold 2 electrons. That energy level can hold 8 electrons. That one can hold 18. And then when you finally get up to here, 32, 32. This could hold 32. It just, we don't need that energy level to get all the way to uranium. To uranium, you might have some electrons in here, but you don't have any in these higher energy levels. Okay. Trying to figure out how to divide you up. There's 4 of you over there. 4. Okay. You guys and the back row will be team number 1. Team number 1. You can kind of work together, work on this by yourself. Make sure you know how to do it. And there's 2 there, so you can't go back. Okay, so team number 1, what I want you to start on is these first 3 here. Lithium, sodium, and potassium. I'm eventually going to write lithium, sodium, potassium on the board. And 3 of you, not the same person, but 3 different ones from your team come up and do each one of those, okay? So what I want you to do is figure out the electronic configuration of those. Here's your chart right there. Figure out that. This is team number 2. The middle ones. See those 3 in the middle? Right in the middle. Fluorine, chlorine, and bromine. The big team. Why don't you work with them? And so this will be the 3rd team. So you guys do the last 3. Do the last 3. Figure out those electron configurations. You're going to come up here and write them on the board eventually. As soon as I get them mapped out here.
Kind start.
Your name?
Tasneem. Thank you.
And you're, I will show you. You're working on that.
And then this jumps to so you start by like writing the element
This side.
and the number of starts with 1S1 and like each sub-level has a certain amount of energy levels that can reach. So S like 2, so it's 1S1 and then 2S1.
Oh, you're in that. Oh. Never mind.
Okay, let's just glance at this for a minute. Remember, I showed this slide on Tuesday, and what this is showing you now here is that here are your principal energy levels. Two rings here is really kind of representing two sub-levels at that energy level. The S and the P. They're not like that, they're not rings, but there's two rings to represent that there is an S sublevel and there is a P sublevel. This is why this energy level can hold 8 electrons. S only holds 2, P only holds 6. If you add those up together, those are at the second energy level, it has that second energy level can hold 8 electrons. But the sublevels still hold that, just still have their regular seating capacity, which is 2 and 6. Okay? All right, now here's what I want to do. I want to take a minute and just make sure all of you have the correct ones written down. Team number 1 did this one, team number 2 did that one, and team number 3 did that one. So let's take a look at team number 1. Now what should be the case here is that the number of electrons they have accommodated here add up to the number of protons that are in this neutral atom. Remember, we've got protons equals electrons. That's the case if we're talking about a neutral atom. No charge right here. We'll be talking about ions today, and we're going to have to start dealing with that. So we should have 2 plus 1 is 3. We should also have the right, the electrons in the right locations. 1s2 fills, and then one more electron goes in 2s1. Sodium has 11. 1s2, 2s2, 2p6. There's 10 electrons. And let me go back to this other chart so we can wrap our minds around what's going on. Okay, so we've got 1s2, 2s2, 2p6. That's 10 electrons. We need 11, so an electron goes right in here, 3s1. Now, all of you should write these down. Once we verify they're correct, write these down, because I want everybody to have a complete table of these today. Potassium, 1s2, 2s2, 2p6, and then we go into the 3s, and it can hold 2, 3s2. We go into the 3p, and it can hold 6. So that's 2 plus 2 is 4, plus 6 is 10, 12, 18, and we need to put 1 into the 4s sublevel. And we get our 19 electrons. Okay, now before we move on, team number 1, look at where lithium, everybody look where lithium, sodium, and potassium are. It's group 1A. These are the alkali metals. We're going to come back and we'll come back and talk about this a little bit more. I wish I had some post-it notes because, and I'm not going to write up there and write on this periodic table, but I want from now on this to be labeled 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. These are the main group elements. And I think the periodic table I gave you can see this here is underneath there. So go by those numbers. 3A, 4A, 5A, 6A, 7A, and 8A. And I didn't write those on there. I want you to know I'm not modifying this to match me. That is the more useful group numbers. And you'll see why in a minute. The 13, 14, 15, it doesn't do me any good. It doesn't tell me anything. 3A, 4A, 5A, 6A, 7A, and 8A does tell us something. Now, go over that. All right, let's look at this. Look where we are in the periodic table. We're way over there, group 7A. These are the halogens. I don't expect you to know the name of every group on the periodic table, but the alkali metals, the halogens, and this one, and group 2A are the four that I expect you to know them by name. That's the halogen group in the periodic table. Fluorine, chlorine, bromine, we go down here to iodine. We don't have to do the whole group to see what we want to see today. All right, so fluorine has 9 protons, it has 9 electrons, 1s2, 2s2, 2p5. That's 9 electrons. Chlorine, 1s2, 2s2, 2p6, that's 10 electrons. 3s2, that's 12, and 3p5 is 17 electrons. That's correct. Good. Bromine. 1s2, 2s2, 2p6. You can see this gets pretty monotonous. They're all kind of starting there. 3s2, 3p6, and then we go to the 4s2, 3d10. Now we're coming in. We've got the 4s2 filled. Now we have to fill the 3d10, and then we have 4p5. And that adds up to 35 electrons. Good. The group 8A. And these are the noble gases. Or sometimes you'll see them referred to as inert. The inert elements or inert gases. Inert means unreactive. Inert. You go to a party and someone's sitting in the corner and never says anything. Are they there? They're inert. They're not interacting with anybody. Well, that's these elements right here. They don't even combine with each other. If you go to HEB and want a helium balloon, take it home to say happy birthday to somebody, it's filled with helium. What's in there? Atoms of helium, gas, bouncing around inside there as individual atoms. They don't even combine with each other. Helium, they're all alone. Individual atoms, neon, argon, krypton, xenon. This is what made them so hard to even know they existed. All of these other elements here, you can dig around. You can go into geology class and they'll show you rocks and they'll say this is nickel oxide, this is copper oxide, this is iron oxide, different forms of iron oxide. This is an iron, copper, oxygen compound. They combine, and they all combine with oxygen. They all combine with oxygen. That's what happens when your car rusts. The iron in your car is combining with oxygen. Your car, all the metal in your car eventually will end up as a an ore somewhere in the ground because it combines with oxygen. So they dig that out of there and they break it apart and they say, oh, it's made up of iron and oxygen. We can actually pull these things out of the ground and discover what they are, but we couldn't do that with these. So these things, it was well into the 1900s that they even discovered some of these noble gases. That's the noble gases. 10. 1s2, 2s2, 2p6. And that's 10 electrons. Argon, 1s2, 2s2, 2p6, 3s2, 3p6. That's 18. 2 plus 2 is 4 plus 6. I'm adding up these superscripts, not these energy levels. There's 2 electrons there, 2 here. That's 4, 6 is 10, 12, and this 6 makes 18. Krypton, 36. We're starting to get bigger numbers. 1s2, 2s2, 2p6. You can follow it right along on that chart. 3s2, 3p6, 4s2, 3d10, 4p6. There's 10, 12, 18, 20, 36. Okay. So now let me just explain. We're going to use this a lot right now. But for right now, let's talk about valence electrons. Equals the electrons in the outermost energy level. And when I say energy level, I mean principal energy level. So the number of valence electrons that an element has equals the number of electrons that are in the outermost energy level. So let's take a look at that. What is the outermost energy level for the lithium atom? What the outermost? 2. So we're looking for the highest energy level number. Not the one closest to the nucleus, the one furthest away from the nucleus. How many electrons are there in the outermost energy level of lithium? 1. There it is right there. Sodium, where's the outermost energy level? How many electrons are there? 1. Potassium, what's the outermost energy level? How many electrons are there? 1. Okay? Right away, you're seeing something. Well, let's come back. Let's go over here. Fluorine. What's the outermost energy level? 2. How many electrons are in the second energy level? 7. 7 electrons. This is the outermost sublevel. But when we count valence electrons, we want to know how many electrons are in that energy level, that outermost energy level. Chlorine. 7. Bromine. 7. We're going to count those 2. They're in the 4th energy level, and these 5. They're in the 4th energy level. This is group 7A. That's why you're going to like these 7A group numbers. That group number corresponds to the number of valence electrons that group has. Group 7A has 7 electrons. Okay, now let's look at the noble gases. Valence electrons. How many? 8. Argon. 8. Krypton. How many? All right, we're not counting that. Those are down in the 3rd energy level. These are in the 4th energy level. 8. Group 8A. We're going to call this an octet. noble gases have an octet of electrons in their outermost energy level. They have an octet. All right? We don't need to go any further than that right now. They have an octet. Luke went up to a very high font size, and I appreciate that, so everybody can see it. But right under here, Luke, you don't need to do this, but I just want to, so there's rubidium. Now look at lithium, sodium, potassium, and there is rubidium, number 37. Now, I don't want you to write the electronic configuration right now. What I want you to do is, don't take a guess, make a prediction as to how it's going to end. What's going to be the end of its electronic configuration?
7s1. 7s1.
No.
5S.
5s1. Look at, we went 2, 3, 4, 5. Okay, 5s1. Well, let's see. Let's see. Okay? So we got 37. So we're going to have a 1s2, a 2s2, a 2p6. Follow me right down through there. We're going to have a 3s2, a 3p6. We're going to have a 4s2, a 3d10, 4p6. Let's count off how many minutes. 2, 4, 6 is 10, 12, 18, 20, 36, 37. Okay? We didn't even do it. We just looked on the periodic table. Now notice potassium is in the 4th period.
Thank you.
Period number 4. What did it end with? 4s1. We're starting to fill that potassium is the element where the very first electron has gone into the 4th energy level. That's where we're starting this 4th period with potassium. 4s1, what do you think calcium would be? 4s2. And it's a 2A, group 2A, and we're going to move along from there. Rubidium, we get down, we get all the way across there, we get to rubidium, it's 5s1. What do you think cesium ends with?
6s1.
And Daniel, what do you think francium ends with?
7s1.
7s1. Okay, you were a little ahead of yourself. It was an S1 ending, but we don't get the 7s1 until we get all the way down to francium. 7s1. Okay. This is ions. That's not the number 10. It's ion. Gotten there. We've mentioned octet. I need to mention octet rule. At the bottom here, one main conclusion is you stand back and look at this. We've only got 9 elements here. There's 92 elements over there. But one thing you could conclude so far is that there is a direct relationship between let's put it this way. There is a direct relationship between an element's location in the periodic table, where you actually find it in the periodic table, and its electronic configuration. I'm going to just abbreviate that as elect electronic configuration. Okay, you see that? You can look at where the thing is in the periodic table and start predicting what its electronic configuration is. All right. I'm not rushing through this because I want it to sink in. I want this to sink in. You got over here to the noble gases, and they have an octet of electrons in their outermost energy level. I told you, we've seen this here. And I told you they don't react with anything. So what is that telling us? Well, they are content with this electronic configuration. Unlike all the other elements, they're not content with their electronic configuration. They will behave in such a way to acquire this electronic configuration. That's the basis for the octet rule. That other elements, and I'm going to show some examples right now, that the other elements, you can predict their behavior, chemical behavior, by seeing what they must do to acquire this configuration. Okay, let's take a look at fluorine. Right here. Fluorine has a 1s2. Now I'm going to erase chlorine so I have some room to work right here, okay? So let me erase chlorine. I'm going to use fluorine as an example. I'll come back over there and use sodium as an example. This is a fluorine atom. Mark, can you, right below where that second red light is, there's a blank. I think you can blank the screen. Try that. There we go. Good. So this is an atom. This is an atom of fluorine. What would a fluorine atom need to do to get this electronic configuration? What, Gene? Add one. Add one electron. Gain an electron. Yes? If it gained an electron, it would get that configuration. But keep in mind, it still has a fluorine nucleus. Nothing's changed in the nucleus. It's got 9 protons. But it now has 10 electrons. So that doesn't make it neon. It hasn't become neon. What has it become? Well, let's take a look at it. Over here, we have 9 protons plus 9 charge. Yes? We have 9 electrons, and there's no charge right there. But now what do we have here? We've got 9 protons, but we have 10 electrons. And if we just arithmetically do that, the 9 of these electrons cancel out those 9 protons. We've got a -1 charge. We have a net charge of -1. And this thing right here is called this is a fluorine atom. That's the name you got on your periodic table. This is a fluoride ion. It's a fluoride ion. An ion is an element that has gained or lost electrons. We're going to see ions with positive and negative charges. This gained an electron. Gain of 1 electron achieves for fluorine the electronic configuration of neon. But it doesn't change it into neon. What's the big difference? Neon has 10 protons in its nucleus and 10 electrons, has no charge, bounces around, doesn't get stuck on anything, doesn't react with anything. Fluorine has a -1 charge. The fluoride ion. The fluoride ion. Okay, let's take a look at sodium. What does sodium need to do to achieve the electronic configuration of neon? What am I doing? Here's neon. Here's fluorine, right next to neon. But what is the very next element past neon is sodium. So neon is sodium's nearest noble gas. Even though it's on the far side of the periodic table, it's the closest in similarity to this. What does it need to do to get neon's 8 valence electrons? Lose one. It's got to lose that. So let's take potassium out of here. So we have a sodium, and it has lost an electron. And its configuration looks now just like neon's. 1s2, 2s2, 2p6. And remember, this is the octet right here. The octet that was in the outermost energy level of neon. So what do we have here? We've got a sodium atom here. 11 protons, 11 electrons, 0 charge. But now what do we have here? We have 11 protons and we have 10 electrons. All right? So by losing, it gains. It gets a bigger number, +1. -10 from 11 gives us a +1. And we don't change the name of the metals. It's still now just a sodium ion. Okay, sodium atom, sodium ion. Magnesium atom, magnesium ion. Calcium atom, calcium ion. We'll talk about these things. So that's the, so what is the octet rule? The octet rule, I've got it on a slide, and sometimes when I say it off the top of my head, it's not verbatim what's on the slide, but roughly speaking, what the octet rule is that elements will gain or lose electrons to achieve the electronic configuration of the nearest noble gas. Okay, it's not a law, it's a rule, it's a kind of a rule of thumb to predict what these atoms are going to do. They're going to behave in such a way to try to get the electronic configuration of the nearest noble gas. Now notice krypton way over there is 36. Here's rubidium 37. There's rubidium 37. Here's krypton 36. So what is rubidium going to do? It's going to lose that one electron, and it's going to, by that, achieve the electronic configuration of krypton. And it would be the rubidium ion. And it would have what charge? +1. +1 charge. It had an equal number of protons and electrons, and if it loses one electron, it's going to end up with a +1 charge. It's going to have one more proton than electrons. And each proton has a +1 charge, each electron a -1 charge. Okay, what else do we have to Well, let's just take another one. Just take one that we didn't do. Let's take magnesium. All right, someone give me the electronic configuration for the magnesium atom. 12 electrons.
Six.
3s what? 2. 3s2. And what is the noble gas that's closest to magnesium? Still neon. Still neon. It's not as close as sodium, but it's pretty close. Over there, and you get the neon. So what does magnesium need to do to gain the electronic configuration of neon? It has to lose both of those electrons. Those are its 2 valence electrons. And it's got to lose both of them. And it's going to be this. It still has 12 protons in the nucleus. But now it only has 10 electrons around it. And notice it ends up with a +2 charge. And it is the magnesium ion. So to leave that off of there wouldn't be correct. Wouldn't be correct to write this like that. That is an atom. There's no charge there. There has to be a +2 charge there for this to all make sense. And let me do one other one over here. Okay, let's move back from fluorine. What's the next element back from fluorine? Oxygen. We'll do this. 2p what?
6.
No.
4.
P4. Daniel, you're trying to be the first one to answer. That's good. Okay, so we got that. So now what does oxygen need to do to be like neon? Gain. It's got to gain how many electrons? 2. And this is going to have 8 protons, and now it has 10 electrons, -2 charge. 99% of the time, when we write compounds, you're going to see oxygen being written. It's got a -2 charge on it. When it's reacting with all those metals, got a -2 charge. Luke?
So, saying all elements, as far as the octet rule, to the next nearest noble gas?
Well, I'll tell you what, Luke. Right now I'm picking on the ones that are very dependable. Okay? Sodium will always act this way. Magnesium will always act this way. Oxygen. We got to get into ionic and covalent compounds, but when they are ionic, these are the kinds of ions they produce. So don't nail me down to always. I'm going to have to ferret out some of the nuances here later, but this is the kind of stuff you can kind of go to the bank on. Okay? These elements that we're talking about right now. So we'll get into some of the nuances. So, did you want to go somewhere with that? Is there? You're just wondering how broadly you could apply this?
Like one in the middle, like cobalt.
No. We'll see that these have. This is why I got 1, 2, 3, 4, 5, 6, 7, and 8. I call the main group elements. Those are a little bit more predictable. When we get into the transition metals, you're going to find, for example, that iron can form 2 different ions, a +2 and a +3 ion. So we have to kind of go another step deeper to start understanding how these things behave. Mark?
So what about like the ones in group 4A? They're 4 away from each of the closest.
Yeah, so is that 4A? 3? No, this one right here, 4A.
Like carbon and silicon.
Yeah.
So like You can add 4, you can take away 4 to get to the closest.
Right, and so what you're going to find is they don't form ions. They end up sharing electrons in covalent bonds. These fluorine is going to almost always be negatively charged. It just needs that one electron. It has a real strong attraction for that one electron. But when you get the carbon, and you say, is it going to lose or gain? It shares. It shares with another atom. Or actually, sometimes 4 other atoms to get those 4. But it still wants an octet, one way, shape, or form. Whether it has to form an ion to do it, or whether it has to share to do it. The octet still guides us a lot. Okay, and these are rules. These aren't laws. Yeah, there are, renegade compounds out there that you go, boy, that didn't follow, that didn't behave the way I would have expected. There are those kinds of compounds. And sometimes those make people billionaires because they can look at this stuff. Look at the way this thing behaves. Yeah. Say that a little louder.
Are you going to accept the shorthand for potassium if we put argon?
Probably.
1s1.
Probably. We'll talk about that in a little bit. Where you can shorten, where you can shorten rubidium. Your name is Andre. What Andre's talking about is you can see that what electronic configuration is that of? Krypton. Over there. So in some cases, when you get down to real big ones like this, they'll write it like this. They'll write it like that. That's a shorthand form. Now, what you have to understand, in these brackets, the only thing that can be in these brackets are a noble gas. You can't just pick any old element and say, I'm gonna say cadmium, and I'm going to put one more electron on cadmium. I don't know what cadmium's is, but we can kind of pretty well predict what krypton's is. So this shorthand version is used only with the noble gas as the shortened form, plus the additional electrons that come after what krypton would have had. All right, so we might mention that again. What else? Oh, here's the other thing I wanted to say. So I'm going to erase a bunch of stuff here and just leave these ions. And I want to show you something. I'm going to leave that ion. Leave that one. Leave that one. Leave that one. Okay, now here is neon. Here is the fluoride ion. Here is the oxide ion. This was the oxygen atom. It is now going to be called the oxide ion. Here's the magnesium ion. Here's the sodium ion. They all have neons electronic configuration. So all of those right there, 1, 2, 3, 4, 5, are isoelectronic. That's one of the terms I didn't put on my list over there that I just remembered. What is isoelectronic? They are different atoms and ions that all have the exact same electronic configuration. All right, they're isoelectronic. So the rubidium ion and the krypton atom are another example of two species that are isoelectronic. Rubidium, when it loses an electron, ends up being just like krypton in electronic configuration. So be aware of that term. Okay. Mark, can you turn this front screen back on for me, please? And let's see where that takes us. All right, so we covered a lot of ground. It's really critical. If I went back to a periodic table earlier on here, what you could see, if I can get back to a periodic table, where is it? I don't have, okay. Get back to a periodic table, you can see that the group 1 elements have a +1 charge. They form +1 ions. They have an S1 ending on their electronic configurations. And francium is in the 7th period, so it's 7s1. And the group 2, which is the alkaline earth elements, form +2 ions. They have an S2 ending. The halogens have an S2P5 ending in their electronic configuration. They always form -1 ions. Okay, so we're seeing this strong correlation between where it is in the periodic table, its electronic configuration. And just to repeat what I said on Monday, but now you might understand why it is the case, metals tend to lose electrons and form positive ions. Nonmetals, up here in this corner, tend to gain electrons and form negative ions. And now you know why. They're gaining electrons driving towards this configuration. Though these are all losing electrons driving towards that configuration. But they can get there easier by just the loss of electrons than it is. Sodium can lose an electron easier and then it can gain 7 more. You know, it only has those 11 protons in the nucleus, so it can't attract 7 more electrons. It gives up an electron. Now, we went through all of this to get the electronic configuration to actually understand how many electrons are in the outermost energy level. Because this is where the chemistry is happening. Nothing happens down here chemically. It's all happening with the outermost energy levels. The electron is either being lost from like sodium atom, or the fluorine atom is drawing in an electron to its outermost energy level. But this is where the chemistry is occurring. Chemistry is all about electrons. It's all about electrons. What?
Whenever like it's in between for us, never